Our last speaker of the session is Professor Ali Javey, who is an associate professor here at Electrical Engineering and Computer Sciences. He's also a faculty scientist at Lawrence Berkeley National Laboratory. His research focuses on the integration of nanoscale electronic materials for various technological applications, including novel nanoelectronics, flexible circuits and sensors, and energy generation and harvesting. Professor Javey, a collaborator of Professor Hu, holds a PhD in chemistry from Stanford.
Okay, well, it's really a great pleasure to be one of the speakers today at this special symposium. So you will hear from Chenming's former students and co-workers and friends, but also I can add a different perspective as one of his younger colleagues in the Department of Electrical Engineering and Computer Sciences. I can tell you that when I started 6 years ago at Berkeley, I was coming from a different department, and whenever you're young, you always idolize others, you look up to others, and when I grow up, I want to be like. Some people say I want to be like President this or Michael Jordan. I said I want to be like Chenming, and because in research, his drive and passion for not only doing always high impact work, but also doing the leading and the cutting edge research in teaching. I have to admit that in my first semester, he didn't know, but I sneaked up into the back of his class without him seeing me or other students seeing me, and I was listening in. I was trying to see what makes him this magical instructor that we all know he is. So with that, I'm going to talk about my work on, so I'm going to talk about the work that we're doing on X on Insulator, and this is really motivated by some of the work that was done here at Berkeley in the late 90s and early 2000 on ultra-thin body silicon, but here the difference is we're trying to replace the top silicon layer with X. So I'm going to start by showing you a slide that I borrowed from Chenming without his permission. And this slide really nicely shows you, of course, the short channel effect that if you're an expert in the field, you're very familiar with. But let me briefly give you a picture of what we have, what are the challenges that we're facing when you scale a conventional MOSFET. You have the gate, you have the drain. The two are competing to control the potential of the channel. And of course, you want the gate to win, and you want it to win big. And for a long channel device, the region near the drain is controlled by drain, but that's fine because far away from the drain, the channel and the source region, the barrier to the source, are all controlled by the gate. So in a long channel device, no problem. You're fine, you have a nice switch. As you bring the drain closer and closer to the source, now you can see that we have a problem. Right at the surface, close to the gate is still winning. But as you go deeper and deeper into your material, you get further and further away from the gate, but you're still pretty close to the drain. Drain wins. And here, qualitatively, you can see the effect. You go from a good switch with good switching behavior to effectively a resistor. So this is a common short channel effect that we have with conventional MOSFETs. And that was really the motivation for the work that was led by Chenming and colleagues here at Berkeley in the 90s to really solve this problem for scaled devices. So two different structures were proposed here at Berkeley, and one was, of course, FinFET, which you heard about. And effectively, the idea here is that you have a very thin piece of silicon, a fin, and in this case, the material is now, all of the body is close to the gate. The other structure that was proposed is the ultra-thin body SOI, and the idea here is similar, that you are cutting off the silicon that is far away from the gate and replacing it with a silicon dioxide, an insulator, and by doing that, you reduce your leakage paths. And this is a nice rule of thumb that you can use for the scaling limits. The thickness of the fin that you need to have to get good electrostatics is going to be roughly 2/3 of the gate length, roughly. This is for silicon. And for ultra-thin body device, it's going to be roughly 1/3 of the gate length. So of course, FinFET, you can see, has some electrostatic advantage over ultra-thin body device. So you can play around with this, put a gate length of 5 nanometer. That's what we should be thinking about, especially academics. And if you do that, then you can see that the thickness of the fin or the ultra-thin body device that you need to have is going to be just 1 or 2 nanometer. So if you think about a device with a thickness of 1 or 2 nanometer, now a lot of interesting effects comes into play: quantum confinement, surface roughness scattering that we didn't have to deal with before. So what we're trying to do at Berkeley is motivated by this structure, the ultra-thin body structure. We're trying to use this structure, but replace the top silicon layer with X, with a very thin layer of X. And X here could be either an ultra-thin layer of 3.5, and we have done it down to 3 nanometer, or it could be a layered semiconductor, and it could be down to a single monolayer of a layered semiconductor, which I will show you. So this is a direction that we started, being motivated by the work of Chenming and others a few years ago. And we do this in collaboration with Chenming. In fact, Chenming has provided us with a lot of feedback and input from all aspects, starting from materials to devices. And I'm going to start with the 3.5 work. And for the 3.5 work, what we do is we use a layer transfer process to transfer very thin layers of 3.5 of our material of choice onto a silicon oxide substrate. And the way we do it briefly is that we grow our active material, in this case indium arsenide, on a 3.5 substrate with a sacrificial layer, which is aluminum gallium antimonide. We pattern etch indium arsenide. We then selectively etch the sacrificial layer. And in this case, we just pick these layers up, and we transfer them onto a silicon oxide substrate. And the resulting atomic force microscope images look something like this. The yellow lines are indium arsenide. The brown is your SiO2 background. So you can now transfer very thin layers of, in this case, indium arsenide onto silicon oxide. So this is a direction that we started 4 years ago, roughly 4 years ago at Berkeley. And at the time when we started this, when we showed the results to our 3.5 colleagues, at that time we only had materials results. There were no device results. The first thing that they said was, well, look at this. You have an amorphous silicon oxide, a single crystalline indium arsenide, and an amorphous layer on top. The interface quality is going to be miserable. That's what they projected. The DIT is going to be miserable. And most likely, you're not going to see any gate dependence, especially for indium arsenide. So the question was, does this structure work? Can we get good transistors out of it? And the short answer is yes. And I will tell you briefly how we do that. But before we do that, the concept is very generic. You can make these XOI out of indium arsenide, as shown here, indium arsenide antimonide, indium gallium antimonide, you name it. As long as you have the right edge selectivity, you can transfer the material to silicon dioxide. You can think about developing wafer bonding processes that others have now started to explore, and really start building all sorts of different devices on a silicon substrate with different material systems. Now, from the SCM images from the TM images that you saw, we have a thin layer of X down to 3 nanometer. You have an insulator, a perfect insulator almost. These are SiO2 or zirconium oxide on top and on the bottom. So effectively, you have a quantum well, close to infinite, in fact, quantum well. If you have a quantum well, then the question is how strong the quantum confinement is going to be. And here I'm showing you a chart of the excitonic Bohr radius of different semiconductors. And the rule of thumb is you get very strong quantum confinement if the thickness, in this case, is less than the excitonic Bohr radius. So for silicon, as long as you're larger than 5 nanometer, structurally, you will not get too much quantum confinement. Of course, you can get quantum confinement induced by the gate fields. For indium arsenide, on the other hand, the Bohr radius is 35 nanometer. So any film that you make below 35 nanometer is going to be quantum confined. And the thinner, of course, the more drastic the quantum confinement effect is going to be. So the question is, can we probe these subbands that are forming and look at the drastic effect of quantum confinement on the band structure, on the band gap of our, in this case, indium arsenide? And if so, how do we do it? The nice thing about the layer transfer process is that you can grab your material, in this case, indium arsenide, transfer it onto any substrate. You don't have to transfer them necessarily to silicon dioxide. In this case, in fact, we transfer them to an optically transparent substrate like calcium fluoride. So now you have indium arsenide on an optically transparent substrate. You can do absorption very easily. You can do absorption studies. And from that, you can look at your band structure directly, experimentally. And that's what we have done here. And here you're looking at the absorption spectra of indium arsenide with different thicknesses, starting from 3 nanometer all the way up to 19 nanometer as a function of photon energy. The onset of absorption, of course, is your band gap or your effective band gap. And from that, you can directly measure your effective band gap, which is basically the spacing between your lowest, your first whole subband to the first electron subband. And you can see that when the film is 20 nanometer, the band gap is roughly 0.4 electron volt. Not exactly bulk yet. Bulk is 0.36. So there is some quantum confinement effect, small, but it's still there. As you make your film thinner and thinner, look at this. The band gap shoots up quite drastically. For a 3 nanometer film, the band gap is about 1 electron volt as measured experimentally. So that was the other issue that we had to answer from the beginning was, would indium arsenide be good enough? The bulk band gap is too small, and we were always criticized that we were not using InGas. We were using pure indium arsenide. Well, and the answer was, we were, looking at the rule of thumb for SOI, you only care about thicknesses that are only 1 or 2 nanometer or 3 nanometer. And at those thicknesses, the band gap of indium arsenide is large enough. So let me show you the transistor characteristics that we can obtain from this ultra-thin body indium arsenide XOI device. In this case, the gate length is about 500 nanometer. And look at this. The current drives for this relatively large channel length is pretty impressive already. Much higher than a silicon MOSFET with a comparable gate length. And getting close to, in this case, we had a 65 nanometer data. 65 nanometer silicon MOSFET. So you can get pretty good current drives even at high gate lengths, and that's expected because the mobility is large. But the problem is your subsurface swing is not very good. Your leakage currents are not very good because we used a body thickness of 18 nanometer. So for the case of silicon, you know that you can make the electrostatics better. You can make the off-state currents better, the leakage currents better by making the body thinner and thinner. And the same is true here. Here I'm showing you the device characteristics for 3 different indium arsenide thicknesses. In this case, it's 13 nanometer, 8 nanometer, and 5 nanometer. And you can see that as you make your devices thinner and thinner, the off current drastically improves, goes from around 10 to minus 6 to around 10 to minus 8. And the subterranean swing also improves from 180 to 125 to 115. And part of this, of course, is because of the electrostatics. The thinner the body, just like SOI, the thinner the body, the better the electrostatics. But the other reason, of course, is the band gap. The band gap is also increasing as you make your material thinner. So now you have 2 knobs that are working in your favor for these indium arsenide devices. Now this subterranean swing is still not perfect, and I will show you a little bit later that now we have improved this, and we can now get 70 or 72 millivolt per decade for our devices by doing proper treatment. So based on this, thinner indium arsenide is better. So you might ask yourself, are there any disadvantages to using thinner indium arsenide? And the answer is yes, mobility. Here I'm showing you the effective mobility of our devices measured as a function of indium arsenide thickness. And you can see that the mobility is dropping, especially when you go to sub 15 nanometer, I would say, it starts to drastically drop. This is a fundamental problem. This comes from the surface roughness scattering that we have in our 3.5 devices. The mobility values are still pretty high. This is the effective mobility of our device. It's still over 1,000 centimeters square per volt second. But you can start to extrapolate this, and as you get to 1 nanometer, you can already predict that the mobility is going to be pretty poor. So that's a fundamental problem that we have to start thinking about for 3.5 devices. And here I'm showing you atomic force microscope image of indium arsenide as grown, epitaxially grown, and you can already see the surface roughness of your as grown film. So this is a growth problem. You cannot make atomically smooth 3.5 devices. So we are fundamentally limited by that. We have looked at the subtertial swing and ways of improving the subtertial swing. And the silicon industry is very familiar with this. You just do a forming gas anneal. It improves the interface quality. And for us, it's the same. If you do forming gas anneal, the subtertial swing drastically drops as compared to no treatment. And here I'm showing you the IV characteristic of one device, black, without any treatment. The swing here is about 110 millivolt per decade. You do forming gas anneal. It's a different device, but it's made with a forming gas anneal. And you can see the swing for this particular device is about 72 millivolt per decade at a VDS of 500 millivolt. These are long channel devices, but now we're getting closer and closer to the MOSFET ideal limit of 60 millivolt per decade. Now, these subtertial swings are very close to untransferred indium arsenide or in-gas quantum well structures that people have grown on 3.5 wafers. So that means that our transfer process doesn't degrade the surface properties. We can still get pretty good transistor properties even after the transfer process. So the question is why and what's so magical about indium arsenide? We are exposing it to different etchants. We are exposing it to different polymeric materials, organic materials, and yet we're getting pretty good DITs, pretty good subtertial swings. So what is so magical about indium arsenide? This is a nice chart that summarizes the conduction band edge, shown in red, the valence band edge, shown in blue, for different semiconductors. So great, from this you can see the conduction band, the valence band, their location, the band gap, and all that. But there is another important information shown on this plot, which is the green line. That's EFS, which is your Fermi stabilization energy. And that's often ignored, especially by us in the device community. And what this EFS tells you is you have native oxides in any material. These native oxides, native defects, these native defects lead to electronic states. The question is, where is the position of those electronic states that you're creating by your native defects, for example, by the surface defects? If you look at indium arsenide, which is the one shown here, EFS is deep into the conduction band. That means that if you form any surface defects, the average energy associated with those defects is going to be deep in the conduction band, not in the middle of the band gap. And remember, we really only care about those defects, those traps that are in the middle of the band gap, at least for the subtertial swing part. So this tells you why indium arsenide has good surface properties, at least from the subtertial swing analysis point of view. It works in our favor. So when choosing a material, not only you care about the conduction band and valence band and their location and the band gap, but you should also think about choosing a material that has pretty good surface properties by looking at the location of EFS. Now, I have talked about the problem with the surface roughness in 3.5 devices, and I have convinced you the need, actually Chenming has convinced us the need for having a body thickness of only 1 nanometer for future scale devices. So how do you get a 1 nanometer thick device and still get pretty good mobility? You can't do that with 3.5s. If you have one atom missing, your mobility goes down the drain. And that goes to, to answer that, layered semiconductors present a new area of opportunity for making new types of devices. In the case of layered semiconductors, you have these individual layers that don't have any dangling bonds, they don't have any surface defects, they're fully passivated, they don't oxidize. Within each layer, your bonds are covalent or ionic, and then you have these sheets or layers, and they are stacked on top of each other by van der Waals forces. So you can now start to imagine if you can peel off one of these layers or somehow grow just one of these layers, you will have a single monolayer without any dangling bonds, without any native oxide, and you can start thinking about making devices that are really at the molecular scale, at least in terms of thickness. There's a whole library of these layered semiconductors. They've been known for decades, especially for lubricants. These layers can slide. They are bonded to each other by van der Waals, so they can slide very easily. They're very good lubricants. But they were not really used for transistor properties, for transistors, until recently. And this was 2 years ago almost, or a year and a half ago, when Andres Kiss group showed that you can make devices out of monolayers of molybdenum sulfide, which is a layered semiconductor with a nice band gap of, it's larger than, the band gap is larger than the silicon band gap. And they were able to show that you can get very high ion, I-off, you can get pretty good mobility. The mobility in this case is for electrons. It's about 200 centimeters squared per volt second. You may not jump up and down at first, but remember, this is a single monolayer. The body thickness is 0.7 nanometer. For 0.7 nanometer, mobility of 200 centimeters squared per volt second is quite impressive. So motivated by this, we started looking at other material systems that are also layered. And one of the materials that we looked at was tungsten diselenide. You can make devices out of monolayers of tungsten diselenide. And people had looked at it before. They made devices, and we made devices also. And this is what people observed before. This is what people published before. And that's what we initially observed as well. The current levels are low. This is current versus gate voltage. It's a poor device. It's not impressive at all. And that was the conclusion. People gave up on it. But the question was whether the poor results come out of the mobility or the contact resistance. We all know the importance of contact resistance. And to answer this, we started looking at different metal contacts. We just started using metals with different work functions. These are p-type devices. By using a higher work function metal, you would presume that you can form a lower Schottky barrier height to the valence band. And look at this. Titanium forms poor contacts, not much current. All of a sudden, you use palladium contact, and now the current goes up by orders of magnitude for your p-channel conduction. So this told us that now we can start to think about devices with reasonable properties. Still, this device, if you extract the mobility, was not very high, but getting higher and higher. So the question was, how do we improve the characteristics even more? We still have some Schottky barriers with palladium. How do we deal with it? In silicon, we know that you have to dope your contacts, your metal contacts, the region underneath the metal contact. You want them to be as heavily doped as possible to make the Schottky barriers as thin as possible. So here, how do you dope? Do you start replacing the atoms? And if so, wouldn't that introduce defects? What would be the right doping approach? So we started using surface charge transfer. This is something that we learned by working with carbon nanotubes and graphene. In this case, we exposed the semiconductor to NO2 gas. NO2 molecules are known to be highly oxidizing. They withdraw electrons out of the semiconductor surface. By doing that, they create holes in the semiconductor. So if you do blank doping, you go from a device that looks like this, that has strong gate dependence, the currents are low, to a device that has weak gate dependence, but the currents are very high. It's now heavily doped. You can extract the doping concentration. The doping concentrations are high enough. They're generally doped for this particular semiconductor. And it's good enough for making now heavily doped contacts. So that's what we did. We started making self-aligned, heavily doped contacts. This is your tungsten diselenide at the bottom. We fabricated a gate stack on top, zirconium oxide gate. source drain to the left and right. There were underlapped regions. We used the gate as a mask to dope these underlapped regions P+. So now you have source P+, your channel P+, and the drain. And if you do that, then you get these beautiful transfer characteristics. Subterranean swing is 60 millivolt per decade. It's a single monolayer. There are no dangling bonds. You get the ideal limit right away. The mobility is 250 centimeters squared per volt second, which is, again, pretty good for that particular thickness. And you get very nice IV characteristics as well, output characteristics as well. So with that, I'm going to conclude so that we can head to lunch. And I hope that I was able to give you a picture of ultra-thin body devices moving forward, not just based on silicon, but thinking about putting other types of materials, replacing silicon with other materials. And there are a lot of opportunities to explore here. You have a wide range of different semiconductors that you can play around with interesting properties. And with that, thank you very much. And congratulations, Javey.
I want to delay your dinner just for one little moment. I want to tell you a little story about Ali. You know, for a long time, I thought that really breakthrough device work will come from electrical engineers, because I felt the physicists and the chemists, although they have a lot to knowledge to contribute, but they could not put in enough time to understand the device, so to take advantage of these chemistry and physics knowledge to really bring out the next generation device. I was very surprised when I read a paper by Ali when he was a student at Stanford. He made the world's best nanotube transistors, short channel, CMOS, and everything just right. What surprised me was that it did not come from electrical engineer. He was a student of chemistry. When I interviewed him as faculty candidate, I found out that he really knew more than most device physicists know. So I have said in faculty meetings that this chemist is a better device physicist than I am, and I really meant that. This is a wonderful combination. Congratulations.
Thank you.